SQL query performance tuning refers to adjusting the parameters at SQL and DBMS levels toward optimizing identified metrics. Main performance tuning or performance optimization targets are the number of input and output operations, utilization of processing resources measured in CPU seconds, minimizing skewed processing, and query runtime. Additional tuning targets are memory consumption and network usage. The computer technology evolution in the 1900s allowed not only to perform accurate calculations at unprecedented speeds but also to store and retrieve data in digital form. The more data is available, the more questions we would like to answer in more detail. The increase in volume pushes the data down the computer memory hierarchy, away from the processor, to allow for larger storage capacity at the expense of slower access time. The image displays the latency for accessing data across a modern processor's 3 cache layers, through the memory bus to DRAM, and across to an SSD or spinning disk drive. Level 1 cache is pricey and restricted. The instructions and the data it will act on are each fetched independently. All information is sent to the core through the Level 1 cache. The Level 2 cache is searched if the data cannot be located within the tiny Level 1 cache. Similarly, the Level 3 cache is checked before DRAM if the data is not in the Level 2 cache. You'll notice that a fetch from the Level 1 cache executes 200 times faster than from DRAM. There is a 1000 times penalty if the data must be retrieved from SSD or disk. Teradata prefetches data into DRAM in an attempt to decrease the 1000 times penalty. By anticipating the required data and prefetching it into the Level 3 cache, modern processors attempt to reduce the penalty between cache and DRAM. The efficiency of data prefetch is decreased if more simultaneous queries are issued against several tables, placing demand on the memory. Additionally, Teradata reduces the overhead by compressing data blocks, called block-level compression, to retrieve more information with each block or cylinder read from the disk. When using block-level compression, each block of data needs to be decompressed before it can be utilized. Teradata offers another method of compression called multi-value compression, which can keep the data compressed for processing we will talk about later in this class. While block-level compression reduces the cost of IOs, it also consumes CPU cycles. Teradata additionally employs cutting-edge vector processing methods. The supercomputing instruction set, which includes SIMD instructions, may be used with vectorized data. Single instruction, multiple data instructions retrieve a single instruction from the Level 1 cache and reuse it repeatedly on the vectorized data without waiting to retrieve new instructions. A query releases the CPU while waiting for data to be retrieved from the disk, and Teradata can launch a new query. The Level 1 and Level 2 cache in each core will most likely be flushed, and new data will be obtained for the longer-running queries, longer than a couple of seconds. Even the whole content of the Level 3 cache may be flushed. In this instance, most of the benefits of vectorization and compression are eliminated. The vectors must be retrieved from Level 3 and DRAM once again. In a situation where hundreds of queries are running simultaneously, the pressure on memory keeps flushing the cache, reducing the advantage of vectorized query processing. Now you will probably better understand that despite all the improvements modern processors bring, access to the slowest component in the memory hierarchy is still the bottleneck regarding IOs. Data can only be processed if it is available in the CPU. This is true for your personal computer as well as a massively parallel computer system like Teradata.